Okay, hello and welcome. Today's episode of Advanced Programming is going to be a short one. We're going to talk a little bit about stacks and queues, and we're going to look at an example of one implementation of queues that supports O of N insertion and removal. And then we're going to look at another one in the future when we go back and talk about linked lists, which are actually the more traditional way of implementing a queue. But first, let's look at what a stack and a queue are and what they bring to the table. So a stack is a very simple data structure that offers you O of 1 insertion and O of 1 removal, and it does this at the expense of allowing you to search or sort. So already I've pre-filled the methods here, and I'm going to leave the comments in there. But today we're not going to be writing the code just because it's so simple. We're just going to follow along with it. A stack really doesn't have a concept of searching. I guess that's where we're going to open up. If you're talking about a stack, the only item that you have access to is the top one. And you can conceptualize this like a stack in the real world, like a stack of papers or something. In order to search through the stack of papers, you have to remove them one at a time from the top. In doing so, you're kind of destroying the stack as you go. You're turning it into something else. So while sometimes you see people talk about something like sorting a stack, what they're really talking about is taking the stack apart, doing something else with it, maybe putting back together a sorted stack. But a stack of paper, you only have access to the top item. You don't have access to any of the items in the middle unless you remove the top item and do this repeatedly. And it's the same for a stack when we're talking about the coding concept as well. And this is what gives us the O of 1 insertion and removal time. We're inserting things only at the top, and we call that operation, instead of an insertion, we call that a push. So a push in stack terminology is an insertion. It's putting it into the next available spot. And we've already basically gone over what push is if we were to implement a stack as an array list. So if our underlying structure is an array or an array list, which is the traditional common way to think of a stack, it's basically an array under the hood, just like array list is basically an array under the hood. Then it's exactly the same as the add method that we have already seen in ArrayList, which just adds something again to the end of the underlying array. Just like in ArrayList, you can implement a stack that grows as it fills up, and so we can use the implementation of ArrayList, which already does that for us under the hood. And we end up with this simple two-liner here. Remember that the extra code on line 53 is just for the display to update correctly. Adding things to the stack is as simple as just pushing something onto the end. So we've already pretty much seen this before. Oops, wrong demo. Pull that one up first. If I wanted to add a bunch of 5s, there they go, and we see that they are adding on to the end. So we've basically seen the same in our previous demos of array and array list. And if I continue to add items, then it's possible to create a stack that expands, or you can have one that's a fixed size as well. Alright, so that's adding things, and then removing things, equally simply, we only remove from the top. And the terminology for this, adding things to the top, was push, removing things from the top is pop. So we are popping an item off the top of the list. We're removing the last item. And there's one other piece of terminology that we should remember, and that's peek. Peek is the same thing as pop, except you don't actually remove the item. So if you only want to look at the top item without taking it off, we call that a peek. And it should be pretty obvious that peek is O of 1 because it's the same thing as accessing an array element. You're accessing the element at the last spot, so the element at size in array list terminology, or in our original terminology with our array implementation, it would be that next spot or whatever it is that's tracking that last available spot minus 1. Okay, well, what about pop then? What's pop doing? Well, pop is finding that spot, that last item, the size in array list terminology, or the next spot minus 1 in array terminology. We're returning it usually, so all the implementations you'll see in Java of pop return the item that was popped off the top of the stack, and then we're just deleting that spot, so we are in array list terminology removing it. Remember that this call to remove is also O of 1 if the items don't have to shift over. And in this case, because we're always removing the last item, there's never a shift of items involved. The items never have to shift to the left because there is nothing to the right of them And that means there's no items to the right that have to shift over. We're always removing the last thing. All the items get to stay in their same spot. So if we look at this in action, we add 0, 1, 2, 3, 4. 4 is on the end. Now, this implementation allows you to remove a particular number, but since stacks don't have a concept of removing anything but the top number, no matter which number you hit on the numpad, it's going to remove the last item, the only item that makes sense to remove in stack terminology. So first it will remove 4, and that's no matter what I click. So it'll remove the top item, and then it'll remove the 3, and then it'll remove the 2, and then the 1, and the 0. And we can see that nothing had to shift over for anything to happen here. And that's it for stacks. We push things on the end, we pop things off the top. It's O of 1 both ways for fairly obvious reasons. So you might ask yourself, why this data structure? What's useful about it? When would I bother with this? And it's simple. It's simple to implement. Its efficiency is great, although the limitations are pretty obvious. And the answer is that whenever you have a bunch of information, that the order doesn't matter. All that matters is that all of the information is processed eventually. All that matters is that the information is maybe processed in the order that it was added, or in the reverse order to the order that it was added. Those are good examples of situations where you might use a stack. So the most common example is the stack that underlies all of your programs. The stack that underlies all of your programs begins at the main method, and then the main method calls whatever next method that it's going to call. So for example, it calls, here it calls the constructor for display. Alright, and then the constructor for display gets added to the stack. The constructor for display calls, well, there's a bunch of things that it calls here, but let's say it calls the constructor for dimension. So the constructor for dimension gets added onto the top of the stack. The constructor for dimension, I drilled into the built-in dimension class that doesn't call anything, it just sets a couple of variables. So here we've reached the end of what we call the call stack. Now, this function can execute. When it finishes, it will be popped off of the call stack. And we will return back to where we were previously. We'll return back to the panel, or display. And then it will continue to execute this constructor. It'll go on to the add mouse listener. It'll execute that, pop it off the stack, go on to the add mouse motion listener, push it onto the stack, execute it, pop it off the stack, and so on until it finishes all of the execution here. Some of these will go a few layers deep too. There might be a call to digit button, which then has to call rectangle 2d.double, and so this will execute, and then that calls set rect, and that will execute. This one actually sets some variables and doesn't call anything else. So this executes, it gets popped, then this executes. This is now at the top of the stack. It gets popped. Then this executes. It's now at the top of the stack. It gets popped. And then finally we're back here. Eventually this constructor will finish. It gets popped too. We go back to, or was it that called the display in the first place? I think that's back to the driver. And then we resume execution from here. And when all of this finishes, then main can get popped off as well, and the stack is finally empty. So because our functions come in a certain order, and we want to execute them in the order that they come in, and then we want to pop the results up as we finish them, and they return different values back to the next function up on the stack. This is a perfect application for stacks. So the only thing that matters is that the order that they come in, they're not sorted alphabetically or whatever, it's just the order that they came in is the only thing of significance. A perfect example of a situation where stacks are applicable. And if you're processing something where order doesn't matter, like a stack of paper, like a stack of mail, that's another example where as long as the entire stack is processed at some point eventually, you can put them in the stack in any order, and you can still efficiently process that stack of paper. In that case, any additional kind of complexity that you add to it, maybe pulling from the middle or sorting them first, is unnecessary. You only care that all of your mail, all of your papers are sorted eventually, so why bother adding complexity to it? So a stack is one of these bare bones, simple data structures that you use in situations where that's what you need, a bare bones simple data structure. Let's move on to queues, which are almost exactly the same thing as stacks. The only difference between a stack and a queue is where the queue pulls from. In English, American English at least, the queue is better known for its more common name, the line. So when you stand in line at the store, the first person to show up is actually the first person that gets to go. The first person gets to check out or whatever. So a queue works in exactly the same way, rather than a stack where the last item that's in is also the last item out. We call this, some people abbreviate it as LILO, or last in, sorry. Last in, first out, LIFO. A queue is the other way around. It's first in, first out. FIFO. You'll see FIFO more common than LIFO. You'll almost never see anybody say last in, first out. But you'll see first in, first out as an abbreviation for basically what a queue is doing, which is that the first person in line is the first person that gets to leave. And we can visualize this before we look at the code. If we add 0, 1, 2, 3, 4, again, no matter which button you click, it's always going to remove the first one in this demo, because there is no concept of removing a particular number. You always remove the first one. So it's going to remove 0, and then it's going to remove 1, and then it's going to remove 2, and then 3, and then 4. And you'll notice in this example that they had to shift over. Alright, so if we go to the queue demo, which is over on the right here, the push is the same as our stack demo. Check it out, identical, because we're inserting onto the end. But the pop is a little bit different. And the pop is a little bit different because we are now taking the item off the front instead of taking it off the back. Remember, we can do this with array lists. We have this get method to return us a particular item at some index. That's still O of 1. That's the same as this one. It doesn't matter what index we're looking for. It's always O of 1 access a specific index, because you don't have to look through all the items to get to one index. But then that remove method, we talked about how this one is O of 1 because none of the items have to shift. Well, that's not true for this one. In fact, this is the worst case. It's O of n every time, because all of the items that are in the array list now have to shift to the left to accommodate for it. And that's why queues are rarely implemented using an array list or an array-like structure like this. A queue is best implemented, or I guess most easily implemented, with something like a linked list, which we'll look at later. And then peek is the same as well. You're just accessing a particular index and returning the item there. So that's the same. You'll also see different terminology with queues. Instead of push and pop, sometimes you'll see NQ and DQ. So that's pretty straightforward and indicates that you're using a queue if you've got the term in queue coming up. You'll also sometimes see the word poll instead of pop, so you're polling the next available item in the queue. And there are a couple other words that you'll see more infrequently, and sometimes people will just use insert and remove and be pretty general with it. I don't actually remember what the built-in Java queue uses, so you can go check that out and see what terminology they run into. But both stacks and queues will usually avoid using, in every programming language, not just Java, will avoid using the terminology insert and remove and use push and pop to be kind of more specific that these are stacks or queues rather than something where you can insert and remove arbitrarily. They have obvious limitations. You can only pull the first and last item. And again, like the stack, the queue doesn't really have a concept of being searched, and it doesn't really have a concept of being sorted. Although it's certainly possible to search or sort them, you can always look at the array that's under the hood. If you're the one that's implementing this, you might need this functionality for whatever reason, and so you'll definitely see even interview questions where they'll ask you something like, how do you sort a queue without adding any additional memory? So sorting a queue in place is a common interview question that you might have. Likewise for sorting a stack in place, or sorting it without adding more than another equivalent of memory. So if you have a 10-item stack, adding another 10 items worth of memory. And basically the problem that they're trying to get you to solve is, how do you pop the items off in a particular order and then push them back on such that they'll be actually in sorted order. So this is a question more about, do you understand how a stack works versus do you understand how sorting a stack works? Because if you understand how a stack works and you understand that you've got to pop all of the items off before you can really begin the sorting process, that's probably good enough to get past that question, although there are some cleverer answers that don't require you to pop the whole thing off. There are some clever answers that you can consume even less memory to achieve. But we won't go into those now. Okay, so if removing from the queue is O of 1, because we have to shift all the items over, is there a way that we can pop things off of a queue, still use an array as our underlying data structure, and also be able to insert and remove from our queue, so push and pop into our queue in O of 1 time? And it turns out that there is, and that's where this week's homework comes in. Now, if you're watching this later than the class took place, the starter and the solution for this should already be available on GitHub. If you're still in class, then just the starter is on GitHub, sorry, but you get to look at what the solution will look like, and hopefully that'll explain it to you a little bit better. So the two circles that you see, they're actually on top of each other. There's a red and an orange circle. Those represent the start and end pointers in our circular array. And this is a regular array under the hood, except that I've drawn it this way in a circle. So you can see the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 inside the inner array, and then there's an outer one, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it wraps back around to 0. This visualization is why we tend to call it a circular array, but I think you'll see pretty soon what makes it circular. So let me try to add a color to it. If you click any of the colors on the top, they add to the circular array. And what happened when I added that color was that the end pointer, the red circle, moved up a spot. If I had a couple more colors, then the end pointer continues to advance. Alright, so a color at a time, it continues to advance. Now, consuming something from the queue requires me to press the space key, and it will change the background to the last color that got consumed. So when I hit the space key, the background turns into the color that used to be at index 0. And the orange bubble, the one that tracks the start of the queue, moves up. So remember, we always pull from the beginning, right? Well, I was able to pull from the beginning. I pulled from 0, and none of these items shifted over. So there was no shifting involved. I'm going to remove 1 as well, and we'll see that the background turned green, but there was no shifting. The rest of the items are still in the same place. And I'll remove 2, and 3, and 4, and 5, and 6, and that pointer continues to advance without any of the other items having to shift. I can continue to add items, and then what happens when I get to here? Well, in array language, this would have gone out of bounds at this point if I tried to continue adding. But obviously what I did here is I was able to wrap around somehow. And so the next item that I add, in this visual, it's very clear to see it just adds to 0 instead, the pointer wrapped around. If I had this as a column instead of as a circle, you would see that pointer jump to the top, right? So it would have been on the last item, and now the next spot to insert into, that red end pointer, has gone back to 0, and I can continue to insert items. This didn't affect the start pointer where items are being removed from at all. Now, this assignment requires you to create a series of circular arrays. So when the inner one overflows, here the inner one has filled up and no longer has any room. You'll note that something is true that was true in the beginning as well. The orange and the red, the start and the end pointers, are now on top of each other again. The only difference between a full circular array and an empty circular array is that the start and the end pointers are in the same place in both the full and the empty one. But in the full one, the start and the end pointers are in the same place and that spot is occupied. And in an empty one, the start and the end pointers are in the same place and that spot is empty. So there's actually an O of 1 solution for checking if a circular array is empty or full if you have access to those start and end pointers, which you essentially need to in order to implement this. So you can check if it's full or empty in O of one time, which is not something that all data structures are able to do. Although all the ones so far that we've looked at are, it's very easy to see if an array is empty or full, if it doesn't have any gaps, like this one does too. Alright, so the next item that I add should get added then into the next available circular array. So that'll get added to this outer one. But if we begin to remove items again, if I hit the space key here, it's going to pull from the innermost circular array that is available. So it will begin to pull from the inside one. And if I begin to add items again, then it will add them to the innermost one that is available. So it will begin to add them again to the innermost one. And there we go. And once that one is full, then again it will resume adding them to the next outer one. And the final layer of complexity that needs to be implemented for this task is that every time the outermost circular array is full, like here, and you go to insert something else, it will spawn a new circular array and allow you to continue adding items as you wish. So it should do that infinitely. And so if I continue to add items, it will spawn more and more circular arrays to hold them. And then if I hold the space key, it'll draw from the middle. Sorry, I should have done an epilepsy warning there, but it'll draw from the innermost spot that's available. And when I resume inserting again, it will begin to insert again in the innermost spot that is available. Eventually, it'll get to this point, and all of these inner ones are full again, and it will start to insert again into the outer layer. There we go. Okay, and then the final wrinkle is that I have added the functionality here for you to change the number of circles in each array. And when that happens, it needs to reset not just the two that you started with, but all of the array lists, or all of the circular arrays that have been spawned so far. So here I'm going to change it to this many circles. I've got a couple settings here, and some of these end up with a pretty cool looking spiral, right? And you can log in as many as you want, and you can also try racing to see how fast you can add and consume items. Make yourself a little Ouroboros there. And same functionality as before. Once that inner one fills up, you start to go to the next outermost one, and likewise hold that space key, pulls from the innermost one. If we start adding again, it starts adding to that innermost one. Alright, so again, if you're watching this after September 20-something, 2022, the solution will be up on the GitHub. If not, then just the starter is that handles all these visuals for you. And you can check that out and see if you can pull off the rest of it. Alright, that's it for today. Thanks for watching. We'll get into some more next time.